Welcome to another informative video brought to you by RealPars. Today, you will learn about VFDs, specifically what they are and when do we use them with automation and PLCs. Before we get started on today's video, if you love our videos, be sure to click the like button below. Then make sure to click subscribe and the little bell to receive notifications of new RealPars videos. This way, you never miss another one. So what exactly is a VFD? Well, it stands for variable frequency drive. They are used for running an AC motor at variable speeds, or let them ramp up their speed to give them a smooth startup. Some people simply call them drives. They work by adjusting the frequency of the motor to adjust the RPMs. To do this, a VFD will actually convert the voltage twice. First, it converts our three-phase AC to DC. This is accomplished with diodes. Then it cleans the DC with a capacitor. Next, it will convert the DC to AC. This is accomplished with transistors acting as switches. Utilizing these switches is what allows the VFD to adjust the frequency that the VFD supplies to the motor. This, in turn, controls the speed of the motor. Now, I know this is a lot of information to take in. Let me compare the internal workings of the VFD with a simple plumbing system. First, let's look at the diodes that convert the AC to DC. This operates like a check valve in a water system. A check valve, like a diode with electricity, only allows water to flow in one direction. The capacitor acts as a water filter to keep everything clean and usable. The transistors act like valves. They turn the flow on and off when needed. This allows the VFD to adjust the frequency of the motor. Now that we have an understanding of how a VFD works, let's see what they're used for. One very common use in industry is to control the speed of a water pump in a water treatment facility. A water treatment plant typically has a constant flow of water coming into the plant. However, if the water demand exiting the plant is lower than the supply entering the plant, then the operator will need to slow down the supply. This is achieved by using a VFD on the AC motor. The operator can monitor water flow and manually adjust the VFD accordingly. Another great thing about VFDs is the fact that they can be controlled with a PLC. Using basic communication protocols that have been covered in previous videos, such as RS-232 and RS-485, PLCs can monitor and control motor speeds using the VFD. This helps make a process like water treatment that much easier and more efficient. This setup can be used in any situation that would benefit from automation. Let's look back at what we now know. VFD stands for variable frequency drive. They are used for controlling the speed of an AC motor. They are also used for ramping up a motor for a smooth startup, or to prevent a heavy load from straining the motor on startup. This is accomplished by adjusting the frequency delivered to the motor. A setup of an AC to DC converter, then DC to AC converter. VFDs are used throughout industry. A common example is to regulate water flow entering a water treatment plant. VFDs allow the operator to control the flow of the pump manually or automatically with a PLC. There are many different brands and features available. If you're looking at using a VFD, just be sure to do your research.
Good morning, everybody, and it's New Year's Day, and we've had a couple of people that wanted to talk about VFDs a little bit. I've gotten a few messages, and they've seen the VFDs that are scattered around my shop. That's the one on my mill there. That is a single-phase input, or technically it's a polyphase input. That would be 2 hot legs. So it's 2 phases. But 2-phase is not a recognized term. It's also known as polyphase. So that's 2 phases of input and 3 phases of output, and that's driving that's a 2 horsepower rated unit. Down here on the door of the lathe, and I use that one to variable speed the lathe. You can see my old variable speed drive in there. That's the old Reeves drive that I took out, and that's I just replaced the hand crank with that's a 10K speed pot for speed reference. And I actually have this needle here calibrated to all the various speeds. So that made kind of a nice little plate there. But anyways, that's what I use to drive the lathe. And I'm, again, 2 phases of input, 3 phases of output. And I took off the single phase motor and put in a 3-phase unit. And that's it there, hanging upside down. Now here's a unit that we use, same controller, and it just goes inside of a cabinet here. And this unit is controlling a blower motor via a photohelic. We use speed reference, high and low switchgear to ramp a motor up and down to maintain positive pressure in a laboratory clean room environment. You guys have probably already seen this. I run that off to the side. Now I like these the SM Vector drives. A couple of reasons. The housing on these is nice, nothing exposed in the back. This is just a heat sink, which is just an aluminum finned heat sink to allow the heat out. And if metal chips or anything get down there, there's no electronics or anything there that are going to get hurt. And also they've got a wiring box built right into the bottom here, so you don't have any open wiring like, I don't know, some of the cheap little Ticos and some of the little Chinese things. You know, after you after you save a bunch of money on a VFD, you got to end up putting it in a box. And what you spend on a box and the Tico, you end up with this big box. You got to find a home for it, and you can just put this on, and it's got the Nemo 1 wiring box already built into it, and all the wiring is enclosed behind this panel here. I like these keypads because they're sealed. They don't have any individual buttons or anything on them, so you get on there with your oily fingers and you got nothing to worry about. These are good little American-made units. Let me talk about the different ways to control. This is set up to remote start and stop. I turn on my switch here. As you can see, I'm ramping up over there. And now we just hit 60 hertz. Here's if I can zoom in just a little bit on that thing. Okay, then we ramp back up to 60 in the forward position. I'm in the forward run position, and now you're running at 60 hertz. Now if I am to just take this thing and I'm just going to cram it all the way through stop and all the way over to reverse, and I'll show you what it does. It decelerates, goes to 0, and then it ramps back up. It's not going to give it a forward or a reverse run command until the motor has come to a complete stop. So the unit is smart enough to know to turn itself off, come all the way to a stop before applying the run command in the opposite direction. That's programmable, very easily done. So you can get real flippy with your switches and not worry about just totally reversing the polarity to your motor. And that's great for tapping, if you're doing some power tapping and things like that. These are momentary push buttons. And this one is on a maintained type control. I use the factory switch here, and it's just the old drum switch, but I'm only using, it's a 3-pole drum switch, but I'm only using one of the poles to activate the VFD. So when I flip that switch, that's what sends me up to drive right there. And at this point, see, our buttons here don't work. But a simple parameter change, which is P100, and I go down to 0 on P100, and now I have start-stop control here. And stop. So, I mean, there's a lot of programs here. P100, input value 1, enter, is your remote source. And your remote source is either going to be maintained contact like this, or like on the lathe, it's got maintained contact with the old drum switch. And this is actually the old drum switch too. I mean, I'm just running a very small Belden cable off of it with 2 conductors in it, just to 1 pole of the 3 available poles in the factory drum switch to operate the VFD. Same there, just run 2 conductors over to that switch, and that one is programmed in to use a speed reference. And speed reference is a programmable parameter, and that the speed reference is a 10K pot. And that's that little potentiometer you see there on the dial. And that's maintained contact. That one over there, momentary contact. Speed reference on that one, I use the push buttons right on the VFD because it's right there. So I just bring my frequency down right there. So I mean, I could very easily program this to run off of, I could have 2 more push buttons. Push one to ramp up, push another one to ramp down. I could have a speed pot here where I could just turn it one way or the other. You know, or just go right off directly off the keypad. Here's another example. We ramped up to a start, and now I'm gonna run it all the way to 100 hertz, and there she is running at 100 hertz, and I'm just gonna hit the reverse button. And typically this is a big no-no on like a 3-phase machine or something that doesn't have a VFD, but you're gonna see the display go into DEC, which means decelerate, which also means within the unit it's using the DC bus to brake the motor. So it's actually applying a electrical brake to the motor, and you'll see a reverse command right here get applied, and it'll just be blinking until the reverse command gets taken. And it happens in the blink of an eye, but it decelerated the motor and applied the reverse command after the motor had come to a complete stop and the braking was finished. And we go back to forward and let you watch that one more time. That was a very fast ramp down and a very fast ramp up, but it changes directions very quickly. You can't even see it at the low speeds. I'm going to take it all the way down to the low speed, 20 hertz, and I'm going to apply a reverse command. It's just literally almost instant. And if you're tapping, that's just what you want. You want to just stop that tap and turn it and get it going the other direction. if I just flip the off switch, so I'm just going to flip it off right now. So it's set to ramp down. So it's not trying to stop a huge rotating mass. So it'll ramp down, and when you turn it back on, it'll actually ramp up to avoid belt slippage or any other lock rotor conditions. And these units are nice. You can make the display whatever you want. Right there, that is referencing hertz. So that is running at 8 hertz at my minimum drive speed there. And here I just have, you can go to any electronics store and get a 10K pot, and they've got nice little knobs you can put on them. But you can hear I'm bringing up my speed of my lathe right there. And she'll go all the way to 2,000. And I've got it set to ramp. Right there it's running at 47 hertz. And if I just crank my knob all the way down, it's going to slowly ramp down back down to my 8 hertz and run there. Say you're tapping, or you want to make a heavy cut during low speed, or you're drilling something large, and you don't want a high speed for that, but you want to be able to remove quite a bit of material, and the machine needs more torque at the low RPMs than it does the high RPMs. Well, the vector controls are going to do that for you. There's 2 types of drives, and 2 ways drives can be programmed. One is called a variable torque, and one is called a constant torque. Variable torque would be used for maybe a blower, because as the RPM increases, so does the load, as the fan is trying to move the air. But a constant torque would be something for maybe a conveyor, where it always has to move the same amount of weight no matter what. So you have to be aware that there's constant torque and variable torque. Also, I think we should probably talk about motors, between the difference between 2-pole and 4-pole motors. Typically, a 2-pole motor is going to be a high RPM motor, and if you try to slow down a high RPM motor, which is usually in the 3,000 to 3,400 range, if you try to slow it down too much, you get a phenomenon known as slip. You've only got 2 poles to drive within that motor, and you've got more of a chance for that motor to slip, and you can't get the torque out of them. But you do the same thing with a 1,700 RPM base motor. Now we're working with a 4-pole motor, and there's less of a chance of it slipping at the lower speeds. So you don't have to boost your vector control up as much. What you want to do with those is, if you still need, say at the lower RPMs we need a bunch of torque, but say we want to exceed 1,700 RPM on the motor. Now this is usually easily done. The rotors inside of a 4-pole motor, which is 1,700 RPM, are identical in every way to the rotors inside of a 2-pole motor, which is the 3,000 RPM. You can overdrive a 4-pole motor and get more RPM and go beyond the rated hertz and RPM of that motor. So you could get 2,000 RPM or 2,200 RPM out of a 4-pole motor that's only rated for 1,700 RPM. Your only limiting factor is your amp draw, and you have to go off the tagged amperage draw off of the motor. As long as you don't exceed that, you're going to be fine. And I've got fans, pumps, blowers, conveyors in service that are being overdriven and running 8 and 10 hours a day with no problems. So for your machinery, don't be afraid to overdrive your motor. Do not overdrive a 2-pole, but overdriving a 4-pole is perfectly acceptable. I will demonstrate one other thing. This thing is We'll go all the way up to, okay, here's a good example. I am overdriving this motor. This is a very old, that is 60 hertz. And that is a antique motor, and it was an odd one. It's with the 4-pole. I checked it. It is a 4-pole motor, but it's only rated for 900 RPM, and I wanted to get a little more out of that. So this is actually the rated RPM at 60 hertz, but I've got this this setup trimmed out, so I overdrive the motor. So I'm going to take it up. We're running it at 100 hertz right now. No troubles. I mean, I've been running this thing for quite some time. Like I said, the only limiting factor on overdriving a motor like this is the tagged amperage on the motor. Don't ever exceed the tagged amperage. And you need to know the difference between service factor amps and amps. Service factor amps is the point where you need to go into overload and alarm and not pull ever any more than that. Service factor amps is basically an alarm condition. Running amps or tagged amps, not including service factor, is normal, and I would never exceed just the tagged amperage. Service factor amps, if it doesn't say SFA on it somewhere, service factor is very easily calculated. You take your running amps or your standard amperage and you multiply it by the service factor of the motor. Now the service factor on the motor is going to be 1.15, 1.2. I've seen them as low as 1.10. So you take your standard running amps, multiply it by your 1.1 or your 1.15, and that's going to give you your service factor amps. And that is the point where your VFD needs to be programmed to go into alarm and lock out, or trip a breaker, or trip an overload block, or whatever. These are programmable for running protection for your service factor amps. So you program into these the ragged edge, right where they're going to trip, and that's all done off your motor data plates. But I thought I would share some of this stuff with you to maybe help you out and help you make your selection of VFDs. Okay? If you've got any specific questions, mainly with these units, go ahead and leave them here on the channel. I'll help you out as much as I can, and I've got books on these things that I can reference and help you guys set these things up if you need it. But yeah, just leave a comment and I'll be happy to help any way I can. Thanks for watching.
Version of Enoscope Analytics. The first thing you might notice when you load up the new version, especially if you're used to the previous versions, is the new white theme, designed to make it easier to view your data on smaller screens and to make the graph information clearer to see. As before, when you log into Analytics, the first thing you'll see will be the current day's consumption at 1 hour resolution. If you wish to view individual clients, you can use the left-hand menu here, and in the client section, all of the client tree beneath your organization will be available to click on. To navigate to. So in this example, I'll go to the warehouse. and you can see that we're now looking at the client warehouse location. And if I want to get back to that top level organization, at the top, I can click back up to my demonstration organization and navigate back there. I can also search for specific clients within that menu to filter that list quickly. If you wish to view data from different date ranges, you can either click on the arrows to go back in time to the previous day, pick out specific date ranges from the date picker here for, say, the previous week, or choose a custom date range by clicking on the first and last day of the range you wish to view. As you'll probably have noticed if you've used previous versions of analytics, the filters for viewing different circuits and parameters are now on the right hand side in this menu here. As before, removing or adding different circuits from the view and then updating will allow you to view the information for those circuits. The different electrical parameters can be accessed in the field section. The resolution of the data can be left on auto if you prefer, or you can choose a more specific time unit to view. And as always, you can look at individual phases. If you're working on a smaller screen or maybe presenting to a client, the filter menu can be hidden by tapping on this button here. As before, we have options to alter how the graph is displayed, if you wish to see the totals rather than individual circuits, as well as to automatically refresh the graph with new data as it becomes available. A new feature here is that you can maximize the graph to fill the available space, especially useful for a display or for use in presentations. The download and print options, also in with this graph menu, you can print from here or download the data as a CSV file, as an image, or as a vector image. You can also quickly share the link to the current display by tapping on this button here, which will copy the link to this view to your clipboard for pasting into an email. As before, if you add more parameters into the graph, such as in this example I'm going to add in power and voltage, the new user interface also works much better on mobile devices. As you can see from our demo here, the graph now fits on the screen better, can be maximized to fill the screen space that's available. The summary information and tabular data scales to fit. The filters are available as they are on desktop by showing the filter menu here, where you choose the amendments you might want to make to the circuits or the parameters that you wish to show, and then tap the update button. If you wish to navigate to different clients whilst on the mobile view, these can be accessed from the main menu at the top here.